So in Catalonia, I had this set up just as a proof of concept. I didn't have any load attached. It was just to see what kind of voltage I was getting, what kind of RPMs, and just that it would work, basically. The turbine is currently putting out 192 watts with a 2.5 meter drop, and I still need to measure the flow rate, but it's about 35 litres per second. The sweet spot, like the top of the power curve, is around 60 something volts at 3 point something amps for 192, 200 watts. The cost of this is still about €40. I call it the $50 water turbine just to be safe. It's actually less than that depending where you get it, but all of these materials are available pretty much everywhere in the world. It's just standard PVC, which I've found everywhere that I've ever been, like, in cities and towns and that sort of stuff. It's a hoverboard wheel as an alternator. That's not going to be so available in developing countries. It's super easy to get in Western countries. You just on a second-hand online or something, eBay or a local classified site, you can get like a whole hoverboard for like 20 or 30 bucks, and it's like 2 wheels, battery, charge control, all that stuff. Like, they're very good units, and the alternator is working very well. It should be good for 300 to 400 watts total, and does really good voltage per RPM. And then the Impala is just a computer power supply, 120 millimeter plastic fan, and that's it. It's some bits of PVC, it's nuts and bolts, and an alternator and a fan. So just a quick walkthrough of how I've been testing this. It's very basic. I've got the 3 phases from the alternator coming through a 3-phase bridge rectifier to convert it to DC. And then I've got a voltage meter just across the DC output. In parallel, I've got a amp meter in series coming through to the load, and then that goes back to the other DC channel. In testing the wind turbines and other things I need to test, I'll be basically doing exactly the same setup because it works really well. The liquid rheostat is just a plastic bottle with a water and washing soda mix, and then 2 stainless steel cable electrodes, basically, one of which just stays all the way in the water, and the other one I can pull in and out to set the load. And then the one that's static just has tape along it so that only the very end is in the water. So when this electrode is just touching the water, it's maximum resistance, minimal current, and then when it's all the way in, almost touching here, it's minimal resistance, maximum current. I don't need to get it exactly the right ohmage. I just need to be able to set it to varying points, and then I read the current going through it and the voltage going through it directly with the meters, and that lets me calculate the power, basically. So all of this is not part of the turbine. This is just a test rig. So obviously you wouldn't use this with a container in a window that you have to pump full. This is meant to go in a river. It's just that there's no drop in Berlin. It's all completely flat. So here at the Cardis workshop they're letting me use, it's been a perfect situation just because I can have all of this right next to the window, next to the river, and do it all in a really super controlled, scientific kind of way, changing one thing, testing it. I'd never have this kind of luxury. Usually I'm knee deep in a river somewhere with everything exploding and just trying to hold it together, let alone getting good data. So this has been really good. So the good thing about hydro turbines is that they produce power as long as there's a water supply 24/7. So this doing 200 watts means it's doing 200 watts constantly, which is about 5 kilowatt hours per day, which is enough to power about 1/3 of a Western suburban home, entirely. So 3 of these will power your house. That can be in parallel if you've got enough volume, or in series if you've got enough flow, enough drop. In a global south developing country kind of situation, this will power a lot more houses than that. maybe, you know, 10 or something, depending on like their power needs. So what's happening here is I've got a submersible pump in the water, which is filling this bucket, which I'll describe in a second, and then use that to fill the tank, and then use this to fill the turbine through this tap here. And when this all fills up, as it has now, turn off the pump, close off this valve here, just some tape, and then the purpose of this bucket, which I've had to reinforce because like I imploded like 5 of these things, like the amount of pressure is a lot more than I thought it was. That's now, as this water drains back out of the system into the river, because there's no valve on the pump, that sucks this air, the last bit of air that was here, out of the system, close the tap. You can see like the pressure this is under, like it's doing a surprisingly good job, but that's what all these like reinforcements are for, otherwise it has happened 5 times. So this is full, this is ready to go. This lever here, these strings go down to just like a flat gate I've got at the bottom, like just like a plastic funnel as a sort of like shape to keep the water in, basically. So I crank this back tight, that blocks off the bottom. When I pump the water in here, fills up from the bottom, fills the system, and then now this is ready to start the siphon. Like I said, in the field, in like how this will actually be used by people, like what I had in the last video in Catalonia and here with this sort of like up, over and down style, like full siphon, that was because in Catalonia I was going over a wall out of a mill run that was being fed by a river. Here I'm coming out of an IBC. I think I'm losing a lot of power to that full siphon system, and in the like actual use case it's probably going to be more like just like a straight pipe, like a little bit of a bend at the end, which basically plugs into like a bit of a river, like some drop in a river, which means that all of this will be unnecessary. All you're going to have is you're going to have like the turbine assembly with the fan and the alternator, and then like some feed pipes in and out, and that's it. So it's going to be simpler than this. It's not going to have any of this testing stuff. You just plug it into a river, fill it up, let it go, and it'll do more power than this is doing. The next phase, when I'm back in Scotland, we'll be plugging it into like an actual river, using it like in the field, find out how it does over time. Like people have sort of like raised concern the plastic fan might not be strong enough, and they might be right. So far it's holding up really well, haven't had any problems with it at all, but it's not been going for months and months. If it does break under actual 24-hour use, then I've got options to reinforce that, and I'll see if those are necessary, see how they work. But this is not the field test, this is the power test. Show the inside of this turbine. Screws just so it doesn't fall apart when it's under weight. So that's her, basically. So essentially there's only one moving part of this. You've got your turbine directly on a shaft through the back to the alternator. It's driving that direct drive. So this is a 120mm standard computer cooling fan. Just plastic, but so far is dealing okay. Haven't had any breakages with it at all. We'll see how it goes over time. As I just loosen this off here. So the assembly method here is quite simple and works quite well. So that's the shaft. So this is coming out of just like a little connector nut here. In here is a bush bearing, which keeps it centered at the front. This is basically just a circle of plastic chopping board. So nylon or PTFE or whatever kind of plastic they use. So just like cut a circle out of that. Just bolts through just to lock it into the center. That's strong, it's good and strong. You want to recess your bolt heads here so that the pipe can come over that, the one that connects to it. And then here you just got just a stack of washers around the shaft, around the thread, and so that sits inside that bush. So there's like this slip between the shaft and the washers, and between the washers and the housing. So it's really low friction, nice and centered, doesn't rattle around too much, super easy to make, costs basically nothing and won't corrode. So using like a bearing or something in there, you'd have to use like a ceramic bearing or something, which, I mean, bleh. So the method for attaching the fan onto the shaft here, I've just got like a circle of plastic, drilled an 8mm hole through both of these. I'll be doing a full build tutorial on all of this. So all the step-by-step how to make it and everything. So the method here is I've got circle of plastic, 2 little nuts and bolts. Those are just so that those heads come into contact with the wings on this wing nut. So the wing nut is locked tight, as tight as I can get it, to this lock nut here, so that it basically can't slip. And then that just hits on there, so as that turns, it drives the whole shaft. That sits in the housing, and the whole thing turns nicely. So the other end here is just got a couple of wraps of insulation tape, and that just goes through there. There's a gasket here, which I'll show you in a second. So that just comes out. You have a washer underneath there. That goes into there, and then that just winds in, basically. So I've taken the front plate off the alternator, and I've drilled a hole in the center of the face and put like a countersunk bolt facing outwards. Onto that I've locked tight a wing nut and a lock nut, and then a connector nut. And then if you can see, I've drilled 2 holes into the face here to take the wings of the wing nut, so that as this turns, it turns the whole assembly. The main reason for that is that this can wobble a bit. So this gets pulled out and tight by the weight of the water on the fan. But see, none of this is like precision engineered. So I don't want to have to align everything perfectly. So this being a little bit wobbly and with a little bit of give means that it basically makes it into a universal joint. So if there's any misalignment between this front bearing and like the alternator, then it's accommodated for in the slight give of that connection there. But it's also super strong and can't slip against the alternator, and you can make the whole thing with nuts and bolts super easy for basically no money. So under here I've got like the gasket to stop air getting into that system. I've got like an 8mm shaft going through a 10mm hole. That's so the shaft again doesn't have to be perfectly aligned with that hole. There's some give in that. And then just to center the shaft in the hole. Here at the back I've just got this connected, super simple, just onto the shaft of the alternator, the hoverboard wheel, with just 2 bits of steel on these 2 threads. I can set this by winding these nuts on and off, and I can set like the y-axis by releasing one side and then just like forcing this over like a couple of millimeters by squishing these 2 together, winding them together, and then locking it off again. So I've got basically like XY positioning on the alternator assembly, just with, again, just some nuts and bolts. I'll show you the gasket. I had to try a couple of different options for getting this to work nicely, and now it's super low friction, super low air intake. In future versions I will glue this down rather than using tape, but it's a test. So basically under here there's the hole coming out of here. This is an old hole that I was using as a air intake, ignore that. So the shaft comes out, comes through the washer, and then there's a O-ring that goes on to there. That sits on the tape that's on there, and it's sort of like it's eaten into the tape a little bit, but that's a good thing because it just forms like a nice sort of like housing for the O-ring on the shaft. Otherwise the thread would let air slip in through the O-ring. And then I've just got a square of closed cell. It has to be closed cell. If it's open cell it'll just suck air through itself. Square that'll just like foam rubber type stuff, which sits over that. And that just sort of like seals on to the O-ring on the top and just stops air from being able to get around it or under it or something. The gate is fairly simple but works really well. This is just a plastic funnel with the nose cut off, which happens to be exactly the right size to fit up inside here. You've got this the gasket, which is built into the pipe assembly, which grabs onto it, and then these strings just pull that tight, and that locks in, and that takes the weight really well. It's just got a cloth hinge on the back so that it doesn't fall off, and so that the in and out in this can like vary like a little bit. This lever system works quite well just for giving this like a good amount of tension. I can get this like nice and tight, but then it locks in so that it can't get pushed out by the weight. There's about 60 kilo of water on that gate, so it needs to be like properly tight. So one of the main kind of improvements that I made on this, so imagine this is like vertical pointing down to the water, was to move the assembly from at the back where I had it in the last video in Catalonia directly over the drop. This seems to help. I increased the downpipe from 125 to 160 millimeters. This was to have more water go through the system, but it didn't really increase that by so much because the 125 sort of throttles it down. It's kind of like a lowest common denominator kind of thing. It kind of goes as fast as the thinnest amount of diameter of pipe will allow it, but it did increase the flow a little bit. The main reason for increasing that is that I was getting quite a lot of cavitation coming off the back of the fan. So I've played around with like nose cones and tail cones of here. This is the cap of like a bottle of spray-on antiperspirant, which goes onto the front there. That doesn't seem to make too much difference. I've tried it with and without. It doesn't really seem to help so much, but it did cut down on the cavitation, but it didn't really increase the overall power so much. The purpose of this sort of increase of diameter here was that when the water passes the fan and enters this larger diameter section of pipe, it slows down. So the liters per second stays the same, but the meters per second is reduced. So the faster the water is moving, the more it like tears off surfaces, and that's where the cavitation comes from. So as soon as it leaves this fan, it slows, and that stops it from separating out from the fan, separating out from the wall, and then it's got sort of like a straight drop to the water. Another improvement that I made was dropping the pipe into the water, because as soon as I increased the diameter of the pipe, basically if I put it under any load, air would get in up inside the pipe and climb to the top and then break the siphon. and the whole thing would stop very quickly. So I increased the length to about 2.5 meters, which gave me some more power. Just because of that, but also that meant I could have the pipe under the surface of the water, so there was no way for air to get in. So I experimented with a few attempted improvements on this. One was to put like a stator turbine in front of the impeller to kind of like direct the water onto the blades. Tried a few things, none of them were pretty, this being an example of how ugly these things came out. So taking this out actually increased the power. So this is either not a good idea or just needs to be done a lot better than this horror show I've got here. The nose and tail cones, as I say, probably help a little, but I don't know that it's enough to make it worth doing, although it's just a bit of plastic, so it's easy. Also in here, I had some polystyrene sort of like just cut to shape to kind of like block up this sort of back section, just so that the water would come through smoothly and cleanly. I haven't had a chance to directly compare with and without that to see how much help it makes, but on the next build I will. And those are the most of the improvements that I sort of tried, the ones that helped and the ones that didn't. As it is now, I can probably squeeze like a little bit more efficiency out of it, but I'd say it's pretty much good to go. So I'm happy to broadcast this design now. I'm happy to start working on the tutorial on full step-by-step, which will be on the website, opensourcelowtech.org, and I will put one of these in the field and have it running for months and see how that goes. But this is ready to make. It's doing the power that I wanted it to do. It's costing what I wanted it to cost. So with this compared to like say a 100-watt solar panel, is that this does twice as much power. Also, a solar panel will produce power for maybe 5 to 6 hours a day. So if you've got 100 watts coming out of it, which means it's running, pretty optimally, you might get 500 watt hours per day. This will do 200 watts 24 hours a day. So about 5 kilowatt hours per day. So 10 times the amount of power per day as opposed to a solar panel. A solar panel in a lot of places will cost you 60 to 80 euro. This will cost 40 to 50. So it's half the price and will do 10 times the power.